Hey everyone, welcome back. I hope you watched the last tutorial about the camouflage using genetic algorithm approach. If not, it's pretty cool. You should go back and watch it. And again, also for future videos, if you want to be notified, go ahead and hit the subscribe button and the notify button, whatever that button is. And of course, while you're there, go ahead and look for the little thanks button that if you're feeling extra generous, that you can use to be generous. Okay, let's jump into today's topic, which is the core essence of this my series, how to code this genetic algorithm in Python. And I want to show you all the nuts and bolts of these genetic algorithms. And of course, I'm going to show you, hey, you don't need to do all that every time, because there are certain libraries that are already available for you to do these tasks. But it's fun to code stuff yourself, so you understand exactly what's going on as part of these libraries. Okay, with that information, let's go ahead and jump in. And the first thing is, again, a quick recap. What is genetic algorithm? These are stochastic methods, as we already talked in the last few videos, where that are designed for function optimization, and they're inspired by the natural evolution. We saw that in the last video, where you select a set of parents and you create children using certain criteria like crossovers and mutations and so on. We are going to do all of that again as part of today's tutorial exercise. Now, how do we code this? It consists of a few steps. That's it. If you're prepared, this is pretty simple. I'm not talking about thousands of lines of code, literally a handful of lines of code. So first, we initiate a population of binary strings with random values. You can do this without binary strings, but in most examples, it makes life easy if you define a population of binary strings and find a way to map this binary string to your real values that you're trying to optimize. Meaning decode the binary strings into real values. One way to do that is just take a binary string and convert that into some sort of an integer, and or take this binary string and convert that into a string, and then convert that into an integer, and so on. There are various ways you can do it, but again, the idea is to start the population of binary strings with random values, and then, like I just mentioned, decode the binary strings into numerical values. And those numerical values go into your objective function, so you can actually look at the fitness. In our previous example, we looked at RGB values, and we looked at the target RGB values, and we just subtracted one from the other, and we said, hey, this is our mean squared value difference, and this is the objective function. So here in some objective functions, that's not as simple as that, right? So you start with these binary bit strings because it's easy to do the crossovers and mutations when you have the binary bit strings. It's not easy if you say, hey, my carbon is 3%, my manganese is 5%. Like how do you deal with those? The easiest way is by working with these binary bit strings. Yeah. So, but you need to find a way to decode them into an actual value that makes sense to you. 3% makes sense to you, which meaning you have 3% by weight of carbon in your alloy, right? So that's what 3% means. So you need to convert that into a real value. So we need to decode it, and then select the best individuals from the population using tournament selection. And tournament selection, like I mentioned in the last video or 2 videos ago, is you draw n number of candidates or k number of candidates from the population. You have 100 people population. You take 10 of them randomly, and then you go ahead and assess the fitness, for example. So that's one way of doing that. And then with those, create a new offspring from the selected individuals using a crossover operation, and then you apply mutation to this. We did some of this in the last tutorial, so none of this should be completely strange to you, especially for my subscribers if you watched the last video. And of course, we are going to repeat steps 2 through 5 until some sort of a stopping criteria is met. Okay, so that's the goal for today. So let's go ahead and jump into the code. And again, as usual, I share the code with you, so look for that in the description. Okay, so let me switch to the code. This is Google Colab again, and I'm not using, you don't need any GPU for what I'm trying to show you. So let me go ahead and connect using just the CPU resources. And I added some text. And in this example, I'm going to define a objective function, which is a Gaussian function centered at 7 and 9, which means after my optimization, the answer should be 7 and 9, right? So it's good if you know what the answer is for these exercises. For unknown objective functions in real life, you don't know what that is. That's exactly why you're using this algorithm. But in this case, we are defining an objective function, a Gaussian function that's centered at 7 and 9. So I know the answer should be 7 and 9. So the steps I already mentioned to you as part of the presentation. So let's go ahead and jump in. And again, nothing fancy, no fancy libraries, just NumPy, importing math to do some basic exponential. So the objective function, or fitness function if you want to call it, it's a two-dimensional inverted Gaussian function. Just inverted Gaussian, a bell-shaped function that's actually centered at 7 and 9. You know how to define that, right? X minus center 1 squared plus y minus, I call this y, x1 minus this squared. So let's go ahead and run this line and move on to the next step, which is decoding. We didn't include this in the last exercise from the last video because we did not encode it to anything. We didn't use binary. We just used regular numbers. It was RGB values in an array. But now let's actually define decode. What do we mean by decode? Well, you have this objective function that we are trying to optimize. And what goes into this objective function? You know, so we are trying to find these values, right? So if how do you tell this algorithm to search certain space? That means we need to define what the low bound is, what the upper bound is for each of these values. For what I called x0 and x1. I'm calling it x0 and x1 because the input that goes in here is just a list of two values. And the first number of the list is this, second number of the list is that. I hope you realize that. In case you haven't, let me explicitly explain that. Okay, so whatever that x value is right there, it can search from minus infinity to plus infinity, but that's not it. Well, let me put it that it cannot search from minus infinity to plus infinity. You need to provide a certain bounds. Let's say we say, hey, go ahead and search between values of, I don't know, 0 and 20. How do you represent 0 and how do you represent 20? How do you represent whatever the bounds are right here? You need to represent that in this binary. So the decode is basically that. You're taking a binary bit string and then you decoding it to real values, and that real value goes into this objective function. So this is the decode function for that. And it's very straightforward. Again, you are defining what the bounds are. Again, bounds can be 0 to 10 or minus 10 to 10, and number of bits. You can represent a value with 16 bits, meaning 0, 1, 1, 0, 1, 1, 1, like 16 of them, or 32 of them. It's up to you. Again, it depends on the type of problem you're solving, but for this exercise, I believe we're going to use 16, and the actual bit string is something that actually goes in here. So let's look at what happens. And the output is going to be decoded, right? So that's what we want. We want that bit string with that many number of bits to be decoded into a value that lies between these bounds. Okay, so that's what's going on here. So let's start with a decoded as an empty list because we need two values decoded. Yeah. So first thing first, let's actually get the largest value that can be represented with a given number of bits. If our number of bits is 16, then the largest value is 2 to the power of 16. That can be represented. I hope you know that, which is 65,530 something, 36. Anyway, so that's the largest right there. Why do I need that? Because whatever the decoded value is down here, I need to rescale it back to whatever the bounds that I'm defining here. I'm sure most of you are thinking, why is this guy explaining all kinds of basic stuff? Because I have a diverse type of viewers with a diverse skill set. So with the expense of making some of you a bit bored, I want to make sure that everyone understands these. Yeah. Anyway, so now I am extracting a substring from the current value, defining the start and end. So we are actually going from 0 all the way to whatever the length of bounds is, right? Whatever the bounds are. And for each of those, let's go ahead with started. This is basically nothing, but when you start off, this is 16 to 32 or something, right? So this is basically, hey, take a value of 16 if my n bits is 16, and go ahead and extract those bits from this entire string. That's what I'm doing. So a substring is that, where you're taking the bit string and you're actually getting the start and end from that bit string. Okay, and then you're just converting that into a string there. Characters join the substring together into a string of characters. So you have these two strings and you're stitching them into one string. Again, I definitely recommend you printing each line and understanding exactly what's going on. And we are converting that into a integer. That's pretty much it. And now our value is basically our bounds right there that we defined, the first one, and here is the second one, plus our integer that we get here divided by the largest, which means we are scaling the value to fall within the limits that we just defined, and that is basically the decoded value. So let's go ahead and run that. Now that you understand decoded, in fact, I think I put these lines just so you understand what that is. Okay. So let's say our test bounds are -10 to 10, -10 to 10. And number of bits equals to 16. These lines don't matter, so I commented them out. And let's generate a test bit string, random integer, right? 0 to 2, which means basically 0 or 1 value. How many of them? These many. Convert that into a list and then decode that. And to decode it, I'm actually calling this decode function right there, so you can see exactly what's going on. So I'm printing both the test bit string and decoded value. Now down here you should see the test bit string and decoded value. If you count this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There you go. So these are for this left hand side, the first value, and these 16, I bet these are 16. These 16 are for these. That's it. Okay, so now we got, so these numbers represent -0.45, -8.44. So if I run this again, now you get a new bit string because we are generating that random. How many? 32 of them. First 16 belonging to the first one, second 16 to the second one, and this is exactly what those are, 5.6 and 1.97. So you know that we are supplying a bit string of size 32 to get these two values right now. Okay, let me comment this out. Now that you understand, what the decoding part is, the rest of the stuff is pretty straightforward because we did this in the last couple of tutorials, which so we're defining the selection first. So they select the best individual for the next generation based on the fitness score. So obviously we need to take the values, put it in the fitness score, and based on the fitness score, select the best ones, right? That's what this function actually does. And what does it do? It randomly selects the k individuals from the populations and performs a tournament selection among them. So the input is nothing but the population, the scores, the fitness scores, and how many, like k, is basically the number of individuals to select from the tournament. That's what this is. That's what this function literally does, and there's not more to explain it. And if you want to understand how this selection actually does, which is fun exercise, I think we should always try to do this type of stuff. So test bounds, like before, -10 to 10, -10 to 10, total number of bits 16. How many people, like population? Let's generate 100 of these 16-bit type of population. So we have our population right there, and we are decoding the population, and we are plugging the decoded value into our objective function to get a score, and our test scores are right there. And then the selection is nothing but we are inputting the population, test scores, and k equals to 3, and basically print it out. So when you run this, it should say from a population of 100, the selected population is this. That's the selected one, based on whatever we have done here. Okay, so now that you know how the selection is happening, again, I'm going a bit slow, but these are all important. Step 1, selection, right, as part of our genetic algorithm. Next step is crossover, and then mutation, and we are done. You guys are good to go. So hopefully, I don't know, maybe 5 to 10 more minutes. Patience. Crossover. It requires two populations, two parents, and R cross, which is the crossover rate, the rate at which you want to do this, the rate of this crossover. We'll see that in a second. So what it does, the output is it creates these two children, right? I think it does. It creates a list containing two children. That's the output from two parents using the crossover operation. You know crossover. You just define the rate, crossover rate, and for that many selected ones, you just swap the values. Okay, the children are created by copying the parents and recombination occurs. So you C1, C2 is basically you're taking the parent 1 and parent 2, and then of course you need random number right there, and then you're just selecting those and then swapping the values. So there you go. And again, I kind of gave you a quick example implementation, so let's go ahead and check it. Let's do crossover rate as 0.9. That's pretty high. And then test bounds minus 10 to 10. And 16 high because for our example we should see something happening, and I'm just printing parent 1, parent 2. All I'm doing is just calling this crossover function that we just defined. So let's go ahead and generate parent. So parent 1, child 1, parent 2, child 2, and go ahead and see how similar these are, and at some point there should be some sort of a crossover. You see 1 and 0 there. It's not the same anymore between these two. So there are some crossovers, and wherever you have this 1 becoming 0, you also see that 0 becoming 1 in the child 2 from the parent 2. Okay, go ahead and study this, but I hope this makes sense. Let me go ahead and comment this out, and now let's go ahead and perform mutation. Mutation is again randomly, you just select something and then you say, hey, I want to change 1 to 0 or 0 to 1. That's exactly, not much more to explain there. So let's go ahead and do this, and I'm pretty sure I have an example here so you can understand. So again, minus 10 to 10, 16, and mutation rate is 1 over how many ever we have this. That's kind of, I think, customary. So let's go ahead and define our mutation rate that, and string before mutation. Is there any mutation here? Oh yeah, there you go. That 1 randomly became 0. That's it. Nothing else. Well, that 0 became 1. So you see how mutation works. Yeah. That's nature, guys. That's basically how evolution works. It's all math. It's nature playing math. Now that we have everything, now we have genetic algorithm that we need to put everything together. So where you the input to the genetic algorithm is the objective function, or the fitness function if you want to call it, the bounds within which you want to search, the number of bits, 16 in our example, number of iterations or generations if you want to call it, and number of populations. How many people do we have, population do we have, crossover rate, and mutation rate. That's it. These are all the inputs, and everything is put together down here. And now we are not doing anything fancy. We are just generating the population. We are taking the best ones by applying the objective functions. Of course, decode is part of it, right? And then for each generation, in how many ever iterations you've selected, like 100 generations, for each of these, do the following. Decode it, get the scores, and once you get the scores, go ahead and see what the best scores are, and pick the best ones. Selected, you selected the parents. Now once the parents are selected, go ahead and get the children by performing the crossover and mutation, and then you get the children down here. That's it. That's what that algorithm does. And now let's go ahead and run it. By defining our bounds as minus 10 to 10, iterations 100, bits, population, blah, 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 all of that, best score, decoded, and print the result. And let's go ahead and run that. And now you see how it's going through different iterations, and it started off with some 83,000, whatever, that's the objective function value. But then after iterations, you see how it's actually going down to 1, 1, 1, 1. Now it's down here, and the result is 7.000, 8.999, which is nothing but 7 and 9. That's what our objective function is. It's centered at 7 and 9, and that's the result. So this is how it actually works. And now let me quickly show you, actually, let's save that for the next tutorial. I hope you understand how this thing works. We'll follow exactly the same thing for optimization problem, almost a real life optimization problem in the next tutorial. And let's do this steps. I'll do a bit less explanation, but then let's get introduced to a library that's easily available to us to perform pretty much the same task. But nothing beats the fun of writing your own code, guys. So I hope you appreciate that. And again, I hope you learned something new in this tutorial, and go ahead and hit the like button if you really like it. And comments always help. Usually the positive ones. If you have something critical, please be nice and put it in nice terms so I can improve upon what you're trying to based on your feedback. Okay, thank you very much, and let's meet in the next tutorial.